Good morning, students. Today our topic is paper 6. Today our topic is paper 6, unit 18. Paper 6, unit 18. Today our topic is paper 6, unit 18. Our topic is paper 6, unit 18. That is substrate control methods. It is substrate control methods. Substrate control methods. Substrate control methods. Okay. Substrate control methods. Today our topic is unit 18, substrate control methods. So that here substrate is control the substrate itself control the formation of stereoselectivity. Substrate itself control the formation of stereoselectivity that we going to discuss in our topic. That means substrate determine the dash stereoselectivity in the reaction. Substrate determine the substrate control the dash stereoselectivity in the reaction. We are going to discussing. Okay, first we are going to discussing reduction of cholesterol to cholesterol 3-1 cholesterol 3-1 cholesterol 3-1. So that's we are going to discussing. So the cholesterol 3-1 structure is C8H11 H17 C8H methyl near methyl double bond cholesterol. So I'm writing this is in the form of conformational chain forms. So here I'm writing A B ring. This is A ring. This is B ring. I'm writing here double bond O methyl and continuation chain is there. This indicates continuation chain. Okay, one is hydrogen. Okay, when this compound reacting with lithium aluminum hydride undergo reduction with lithium aluminum hydride. Undergo reduction with lithium aluminum hydride. So lithium aluminum hydride introduce release H minus ion from two ways. One is axial, one is equatorial side, one is axial side. When it is a lithium aluminum hydride release hydride ion from equatorial side, there is a methyl group is there. There is a steric crowding in between the methyl group at here axial position and the introducing hydride ion. Therefore, due to the steric crowding, that forms a less stable product. Well, it is in case of lithium aluminum hydride release hydride ion from axial side, then that there is no steric crowding between any groups in the molecule. Therefore, the lithium aluminum hydride introducing hydride ion at the carbonyl carbon from axial side. Therefore, that due to the presence of methyl group on the structure, that hydride ion releases lithium aluminum hydride ion releases to axial side. Therefore, this the structure is itself control the formation of diastereomeric compounds. Therefore, we are studying in the substrate controlled method. We are studying in the substrate control method. This is the major product is the formation takes place. Okay. So next example is synthesis of synthesis of diastereomeric 2-methyl narbornone 2-one. Synthesis of diastereomeric 2-methyl narbornone 2-one. So for this compound, the starting material is narbornone 2. Narbornone 2-one. When this compound undergo reduction with methyl magnesium bromide in presence of dry ether, undergo reduction with methyl magnesium bromide under dry ether, dry ether. So that methyl magnesium bromide organometallic reagent introducing that methyl carbon ion from exoside. From exoside is the major, endoside is the minor. Therefore, why I'm explaining this, exoside is major, methyl group on exo is the major, ethyl group is exo on the major. Okay, so this is a major. Why? Because of this major means when first that methyl magnesium bromide ion approaches from endoside, yet the hydrogens are there. These two hydrogens, there forms repulsions takes place due to the repulsions between these hydrogens. This methyl magnesium bromide releases methyl from endoside. So here two hydrogens are there. There is no steric crowding. Therefore, this is the endomethyl group is the major product. Okay. So now this. Next one is so next one is going to 1,2 asymmetric induction. One comma to asymmetric induction. First, what is asymmetric induction means? Asymmetric induction means formation of chiral center. Formation of chiral center in the molecule. That molecule is already consist of one chiral center. So that is the asymmetric induction. What is asymmetric induction? Formation of chiral center in the molecule is a asymmetric induction. So 1,2 asymmetric induction means 1,2 asymmetric induction means one chiral center at first position, at second position asymmetric new chiral center was introduced. Okay, just example I am here. Large methyl small. Okay, this is we are assuming this is a chiral center. This is a chiral center. So this is a first position. We are assuming first, second. At chiral center second position. At first position, we are introducing another chiral center. We are introducing another chiral center. That is 1,2 asymmetric induction. So to explain the asymmetric 1,2 asymmetric induction, so Krams is the scientist. Krams is the scientist. Krams is the scientist. The scientist discovered three methods. Scientists discovered three methods. One is Krams open chain model, Krams cyclic model, Krams dipolar model. Three models are there. Krams open chain model, Krams cyclic model, Krams dipolar model. Three models are there. We are explaining it one by one with the models. Okay. First, we are going with Krams open chain model. First one is Krams open chain model. Krams open chain. According to this Krams open chain model, in the asymmetric 1, 2 asymmetric induction. In the 1, 2 asymmetric induction, in 1, 2 asymmetric induction, at the chiral center, there is no lone pair groups and electronegativity groups. Okay, in 1, 2 asymmetric induction, in Cram's open chain model, in 1, 2 asymmetric induction at chiral center, if there is no lone pair groups and electronegativity groups, this Cram's open chain model is applicable. Here I am taking one example here. Carbonyl, medium, large, small. Okay, in this case, in this example, there is no electronegativity groups or lone pair groups. Therefore, this is a come under the Cram's open chain model. Okay, when this compound reacting with organometallic reagents, this is the organometallic reagents. When reacting with organometallic reagent, that so when this compound, first this molecule we are writing into Fisher's Sar's formula. Sar's formula. This is when observed from bottom side. Observers see the molecule from bottom side. Therefore, this is a front carbon, large, medium, small, and this carbonyl and R. Okay. So in the Cram's open chain model, the scientists discovered some rules. There's some rules. According to these rules, at chiral center, large group at chiral center, and group attached to carbonyl is eclipsed. What is at chiral center, large group and the group attached to carbonyl is eclipsed. These are the eclipsed. Okay, and second point, large group at chiral center and carbonyl are anti to each other. Large group at chiral center and carbonyl are anti to each other. Yes. And third point is, and the carbonyl is flanked in between. Medium and small groups. The carbonyl is flanked in between medium and small group. When this carbonyl, when reacting with organometallic reagent, when this metal reagents, that nucleophile releases from small group side only. The nucleophile releases from small group side only. The nucleophile is released from small group side only. Therefore, R and medium, that is, again I am writing R here and OH here R. Okay, I am convert this is the this eclipsed. I'm converting into Fisher formula. I'm converting Fisher formula. When this converted into Fisher formula, R, these are the R's, and OH is right side, and medium, yes, small, and R. So this is the product formation takes place. Okay, this is a Cram's open chain model. Okay, next I'm explain with another example here, specific example I am taking here. In this example, so at the chiral center, there is no lone pair groups, and that chiral center there is no lone pair groups and electronegativity groups. Therefore, this molecule, this 1, 2 asymmetric induction come under the Cram's open chain model. Okay, when this molecule I am converting to the first formula, phenyl, this is hydrogen, here methyl, and the hydrogen. Okay, so according to Cram's open chain model, large group, this is a large, medium, small. Large group at chiral center and group attached to carbonyl are eclipsed. Okay, eclipsed, and medium and small groups are flanked. The carbonyl is flanked in between medium and small groups at chiral center. Yes, this is satisfied. When this compound reacting with methyl magnesium halide. So methyl methyl carbon and introducing the carbonyl, attacking under carbonyl from small group side only. Okay, small group side. Then the product is phenyl methyl hydrogen. That methyl attacking here, OH here, and hydrogen. I am writing this is into our Fisher formula. I am writing this Fisher formula that I am going to methyls are eclipsed. So I am converting to methyls are eclipsed. Methyls are eclipsed. I am rotating methyl here and OH here, hydrogen here. So I am writing the Fisher formula. So here methyl and methyl, and OH is left side. I am writing, and phenyl, OH is and hydrogen here, hydrogen. This is a product formation in the Cram's open chain model. Next, Cram's cyclic model. In this Cram's cyclic model, at chiral center, in 1,2 asymmetric induction, at chiral center, if there is a lone pair groups, then that 1,2 asymmetric induction come into Cram's cyclic model. Okay, in 1,2 asymmetric induction, at chiral center, if there is a lone pair groups, that 1,2 asymmetric induction come under the cyclic model. So lone pair groups example is hydroxy groups, amines, etc., etc. Okay, these are the lone pair groups. This is come under the cyclic model, Cram's cyclic model. So I'm going to discuss with the one specific example. I'm taken one specific example here. Phenyl, carbonyl, hydroxy, methyl, phenyl. At chiral center, lone pair group is there. Therefore, this molecule come under the cyclic model. I am converting this molecule to Sahar's formula. Sahar's formula. OH, phenyl, methyl, carbonyl, here phenyl. Okay, yes. Now, in the Cram's cyclic model, Cram's propose some rules. According to these rules, okay. So lone pair containing group is must be eclipsed with carbonyl oxygen. Lone pair containing group must be eclipsed with carbonyl oxygen. Lone pair containing group is must be eclipsed with carbonyl oxygen. Carbonyl oxygen. Then that nucleophile undergo addition with carbonyl carbon from small group side only. The nucleophile undergoes addition from small group side only. Here I am taking methyl magnesium halide and dry ether. That is it. So here plus minus this methyl here attacking from small group. In this case, the small group is methyl is a small group attaching from methyl side only. Then that product I am writing here OH, phenyl, methyl, and this is here OH, methyl, and phenyl. I am writing to eclipsed formula. I am converting eclipsed. Formula. Then OH, methyl, phenyl. I am rotating here methyl, here OH, here phenyl. I am writing our Fisher formula. I am converting to Fisher formula. That is, so methyls are vertical, phenyls are and hydroxyl group are horizontal. This is a Cram's cyclic model. So according to Cram's cyclic model, Cram's proposed some rules. According to these rules, at chiral center must be lone pair groups are chelating groups, and in Sahar's formula, that the chelating group or lone pair containing group is must be eclipsed with the carbonyl oxygen, and that that nucleophile addition undergo addition at carbonyl carbon from small group side only. Its corresponding diastereomer is major. This diastereomer is major. Next one is Cram's dipolar model. Third one is Cram's dipolar model. Cram's dipolar model. According to this Cram's dipolar model, at chiral center, electronegativity groups are present. According to Cram's dipolar model, at chiral center, if chiral center containing electronegativity group under 1, 2 asymmetric induction, that is come under the Cram's dipolar model. Okay, at chiral center, if lone electronegativity groups are present under 1, 2 asymmetric induction, it is come under the Cram's dipolar model. Okay, Cram's dipolar model. I am taking this is the one, and here I am taking specific example here. Halogen, ethyl, hydrogen, N-butyl. Instead of halogen, I am taken chlorine. Okay, so I am converting to Sahaj. This is I am converting to Sahaj formula. Chlorine, ethyl, hydrogen, carbonyl. It is N-tertiary butyl. Okay, so I am converting. I am rotating this molecule. So I'm rotating in the molecule. So like this. Okay, according to Cram's dipolar model, the group at chiral center, the electronegativity group at chiral center, is anti to that of carbonyl oxygen. The electronegativity group at chiral center is anti to that of carbonyl oxygen. Okay, your oxygen and halogen are opposite is there, anti to each other. Therefore, this is a Cram's dipolar conformer. Cram's dipolar conformer. Okay, when this electronegativity group and carbonyl groups are anti to each other in Sah's formula, at the carbonyl carbon, electron deficiency increases due to this conformation. That means the carbonyl, oxygen, and chlorine at chiral center anti to each other in Sah's formula. Due to the conformation, the carbonyl carbon having more electron deficient. Therefore, when we added methyl magnesium halide nucleophiles, these nucleophiles undergo addition to the carbonyl carbon from small group only, from small group side. Therefore, the corresponding diastereomer is major. The corresponding diastereomer is the major. N methyl, here OH, here N tertiary butyl. So N tertiary butyl. So I'm writing this is into our I'm writing into our Fisher formula. I'm converting to Fisher formula. Before I'm converting to Fisher formula, I'm writing into changes takes place. Here chlorine, hydrogen, ethyl. I'm rotating N-butyl. So I'm writing N-butyl and methyl, here ethyl. So I'm writing this is when a formula ethyl, methyl. Ethyl is hydrogen and ethyl. That hydrogen with chlorine and methyl. So these are the this is the major diastereomer. This is the major diastereomers. This is a Cram's dipolar model. Okay, simply you remember that in Cram's open chain model at chiral center there is no lone pair groups and electronegativity groups. And Cram's open chain that in Cram's cyclic model, in there is a chelating groups are lone pair containing groups at chiral center. And in case of Cram's dipolar model, there is a electronegativity groups at chiral center. This is, and fourth one is Felkinon model. Felkinon model. According to this Felkinan model, this Felkinan model is applicable extension of this Felkinan model, extension of Cram's open chain model. Open chain model. The Felkinan model explains to extra information about the Cram's open chain model. According to Cram's open chain model, at chiral center there is no lone pair groups and electronegativity groups. So when I'm taking here one example. So according to this rule, according to Felkinan model, the carbonyl is placed at a right angle. Carbonyl is placed at a right angle. Okay, carbonyl is placed at right angle. That means large group at. I'm writing this molecule into a Sahaj formula. Right angle means 90 degrees of separation. Or large, small, medium. Okay, large, small, medium. This is the Felkinan model. Okay, this is a Felkinan model. That means the large group at chiral center, must be 90 degrees of separation, 90 degree of separation, 90 degree of separation with respect to carbonyl oxygen. Okay, that means large group at chiral center and carbonyl carbon are 90 degrees to each other. This is a 90 degrees of separation. This is a 90 degrees of separation. So when we are added nucleophiles, the nucleophile undergo addition at carbonyl carbon from small group side only, then corresponding product is the major. I'm writing here R small, R large, R medium. Here OH, or this is a methyl and R. So this I'm writing into eclipsed formula. I'm converting to eclipsed here. I'm converting to eclipsed. R large, R small, R medium, then ROH, R methyl. This is a eclipsed conformation. This is a Felkinan model. Okay, what is a Felkinan model? So in according to Felkinan model, this Felkinan model explains the Cram's open chain model. According to this rule, large group at chiral center, and carbonyl carbon are separated by 90 degrees of separation. Large group at chiral center and carbonyl carbons are separated by 90 degrees, and the nucleophile attacking at carbonyl carbon from small group side only. So I am taking another example to explain Felkinan model. Tertiary butyl, carbonyl, methyl, phenyl, hydrogen. This is the compound. So or alpha methyl benzyl tertiary butyl ketone. This is the compound. So I'm converting to class formula. Class formula. Here methyl, phenyl, hydrogen. So when now it is converted to Fischer Sahar's formula. Methyl and N-tertiary butyl. So what is large group at chiral center must be 90 degrees of separation. I'm writing like this. This is 90 degrees of separation. Phenyl and here hydrogen and methyl. Okay, when this compound undergo addition with methyl magnesium halide from attacking from opposite to that of large group side and to small near to small side. So like this attacking takes place, then forms methyl, here N-butyl, here phenyl, hydrogen, methyl. I'm converting to eclipse. I'm converting to eclipse. I'm converting to eclipse. Sorry, this is OH. I'm converting to eclipse. For conversion of eclipsed methyl phenyl hydrogen, here tertiary butyl, here methyl, here OH. So for Fischer, methyl tertiary butyl, tertiary butyl, and a methyl tertiary butyl. One is phenyl, one is hydrogen here to OH, here methyl. This is a major diastereomer, is the product. Okay. This is the Falkenhayn model. Okay. So in this today topic is that Cram's rules are very, very important. 100% important question. Cram's rule, Cram's open chain model, Cram's cyclic model, Cram's dipolar model, and Falkenhayn model. These four methods are very, very important today topic. Okay, thank you. So I'm sending you notes already regarding to this asymmetric synthesis and synthetic strategies also. So okay, almost I'm sending all the 4 blocks of this unit, this paper. Okay, thank you.